Hey everyone, welcome to 197 Concepts. In this video, I'm going to discuss with you how to check whether a given number is a positive number or a negative number. Okay, so without any delay, let's jump into the video. Let me just set these things a little bit. Yeah, okay. So before going into the program, you have to know some basics about the signed and unsigned numbers. For example, let us say I'm having a number which is 07. Okay. Now, this in the binary format can be written as 0000, and for 7, it can be written as 0111. Okay, so this 0 is having four separate digits and this 7 is having four separate digits because of 8421 code. You can call this as the binary code or the in a more what we say non-technical language, you can call this as 8421 code to be more clear. Okay, so now what you have to observe here is this is the MSB and this is the LSB. So let me write this. This is the LSB and this is the MSB. You might be familiar with the MSB and LSB. So this is most significant bit and this is the least significant bit, starting from 0 and all the way up to 7. Yeah, 0 to 7, that will combinedly make this as 8 bits, right? So in these 8 bits, the highest bit, which is here in this case, is bit number 7. Bit number 7. This thing is called as most significant bit. Now, in order to find the sign of a number, whether it is a positive number or it is a negative number, you basically focus on this most significant bit, which is, so here we are having two separate cases. So this most significant bit can be logic 0, and it can be logic 1. Okay, so those are the two states that we have in binary language, and so most significant bit can be logic 0 or it can be logic 1. Based on this, you tell whether whether a number is a positive or a negative number. If the most significant bit is logic 0, then that number is a positive number. If it is a if it is logic 1, then we have a negative number. Now, when you consider this case, so here you have observed that its most significant bit is logic 0. If I want to write, okay, minus 70, then this can be written as 1000, okay, 0111. You might ask me, this goes to other number, right? If you observe here, this will be the hexadecimal value 8. Okay, it's not like that. When you are going for the sign, the maximum bits that you can use are 0 to 6 itself, whereas the most significant bit 7 is reserved for its sign. Okay, that's the case. So when you are having 8 bits, you can represent from, so a total of how many numbers? This one is 16 and this one is 16. So a total of 32 combinations you will be getting. Okay, but when you go for when you go this one number might be wrong. Okay, don't fix to this number, it's just an example. Okay, so but if you are getting reduced by one bit, you are having access only to 0 to 6 bits. Okay, so the maximum number of changes you can get from these 6 bits will based upon, I can say, 2 power 6, I believe. Okay, so if it is 4 bits, then 2 power 4, which will be definitely 16. Now, if that was 2 power 8, okay, if that was 2 power 8, so we were having 8 bits, that will be 16 into 16, so square of 16. Now, how many bits I am having? 2 power 7, so that one will be some exponential value. You have to, let us see that. Let's see the calculator once. Okay, so 2 to the power of square, that's square. Okay, I don't want square, I need more than square. Okay, for your easy purpose, let me multiply this. How many times? 4 times. 2, 3, 4. Right? That's 16. 5, 6, 7, 8. So 256 combinations you will get. So 16 by 16 is 256. Yeah, we can do this simply. 16 by 16 is 256. Okay, so you will get 16 multiplied by 16, it's equals to 256 combinations. But when you are going for signed numbers, you are having only 7 bits. Then in that case, how many digits can you represent with in the binary form is 1, 2, 3, 4, 5, 6, 7. That's 128 bits. Okay, so 128 combinations, not bits. So that's 128 combinations you can represent with this 2 power 7. That means a total of 7 bits. Okay, so starting from 0, 1, 2, 4, then 8, 16, 32. Okay, so these are the 7 bits. The other bit that we have, the 64th bit. Okay, if you are considering the complete 8 bits, out of these 8 bits, the 64 is reserved for sign. I hope you have got the point. Okay, so that's the main thing you have to observe here. That's a very important thing that you have to observe here, and based on that, we are having our program. So now let me open this. This is much better when you compare to the whiteboard. So now when you see here, yeah, I forgot to thickness. Yeah, this one will be great. Uh, Yellow visible? No, it's better if I take some other color. Let's go with purple. Yeah. Okay. If you observe here, now, if you observe here, so this is just the heading. No need to worry about this. Now, the next one is assume CS colon code segment and start. These are the basic lines for starting again. MASM program. Okay, now and the last lines are done. This is a separate label that I have made, and this is very useful when you come for the exam. When you come for the program, you will get a clear understanding. Then I have used the int 03h interrupt, which is nothing but a breakpoint interrupt, and the ending of the code and the ending of the start label. Now, my whole program depends only on these 3 lines. Okay, so not these 3 lines. The only one line that in program depends upon is the test function. Okay, the complete function depends on the test function. The complete program depends on the test function. Okay, so what is this test function is nothing but this test function will carry out the logical and operation between two variables. Okay, so it's going to carry out the logical and operation between two variables. In our case, these variables are nothing but our required number. Yeah, you can say it as the required numbers. So why I'm saying this as a required numbers is, see, first of all, I'm going to take any number, say like number 20. Then I'm going to make this number 20 and logical and operation with a specific number, which is nothing but the 80. Okay, so this is an hexadecimal number 20h and this is an hexadecimal number 20h. Now, if you write this in the binary form, so 20 will be written as, I'm just considering only the 2 digits. I'm not going for the 16-bit configuration. I'm just going for the 4-bit configuration. So 0010. Okay, now then what we have, it's 0. That means 0000. Now I'm going to take a number 80, and for this I'm going to write the binary form. So 8 is 1000. 0 is of course your 0, 0, 0, 0. Now I am going to do the logical AND operation. So logical AND operation will only result logic 1 when both the inputs are at logic 1. Since no logic here is at logic 1, so this is 0, and this one is 0, this one is also 0. Of course, this one is also 0. When you observe this bit, which is the MSB of our two numbers, if you do the logical AND operation, it goes for 0. Okay. Now you might have seen that the result is all completely 0. This is not my concern. This is not my concern. My only concern is this MSB, most significant bit. Now here it is logic 0. Then it is definitely a positive number. If it was logic 1, then it would have been a negative number. So for that, let us take a different number. So since I have restricted the most significant bit for the sign, I cannot use the number 20, or I cannot use the number above 7. That means I cannot use 80, right? I cannot use the number 80. If I go for 80, let's go for 80. Okay, so this is my testing number, and I'm going to use this 87H, the number that is present in the program itself. So what I'm going to do is I'm going to write 8 and 7, and its binary form is 1000, whereas for 7 it's 1111. And again, our standard 80 number is 1000. Then what I'm going to do is 0000. I'm going to do the logical AND operation. Of course, this comes as 0, and all these will come as 0, but this comes as 1. Then this most significant bit is logic 1. That's why it's a what we call it's a negative number. Now you might ask me, what is the we are using a number 87. Here we are using a number 87, but uh, it's not actually 87. It is limited up to this, only this 86th bit if you count from 0. So this binary representation is limited up to the 6th bit itself. Okay, so that's why it's not 87, it's something else. So when you convert this 87 into into decimal, this is actually a hexadecimal form. When you convert this into the decimal form, you get some other number. For that, you can check out the other video, which where I have described or explained you the difference between hexadecimal and decimal numbers, and the gap between these two numbers. Because what we see as 87 in hexadecimal is not the 87 number in our regular mathematical numbers. It's something else. Okay, na? Because in hexadecimal you are going to count from 0 to 9 up to those numbers. In decimals also you are having 0 to 9 itself, no doubt. But when you are coming from A to F in hexadecimal, there is a change here in decimal. In hexadecimal you use a to f, whereas in regular decimal numbers you make them as 10 to 15. So there is a huge gap. For this you can check out that video. It You will get a clear understanding. Okay, so I hope you have got the point of how to check whether a number is a positive number or a negative number. Now you might ask me, why only the number 80h? Okay, see, let me clear all this. Here you can see I have written a comment line. Try 07H and 87H. So if I have yeah, it's for checking the number, it for taking the number. Okay, like I have told you the example of 20, and I have told you the example of 87. What you have to observe is, as the test command you are using only the number 80h. Now tell me a number that in the most significant bit has to be logic 1, and whatever I have, I don't care those numbers. Okay, if it's 8, no problem. Also, see, let me write the positions. Okay, now 0, 1, 2, 3, 4, 5, 6, and 7. My only concern is this most significant bit. It has to be 1. I don't care of whatever the logic is at all the remaining bits. Okay, if it is logic 1, consider, let us assume that apart from the bit number 7, I'm having bit number 6 as logic 1. Now, what my output, what my binary number will be 11000000. In this case, if I take the number 87 and do the logical operation, let me write the binary form 00, okay, then 00, sorry, it's 7, right? It's 0 1 1 1. Now, when I do the logical AND operation, it's 0 0 0 0 0 0 0, and then what we get here? Here we get 1. Okay, now. So what I'm trying to tell is here we are having the same number, so it's not a big problem. If I had like 8 plus 4, 12, 12, right? For 12, what we get the number A, B, C, right? C is 11, A is 10, B is 11, and C is 12, right? If I had C7 number. Now, if I had here also 1, then my result is going to change. Okay. So what I'm trying to tell is my only concern is most significant bit. Then why do I have to take some any other number? For that, I have to keep in mind the bit number 7, the bit number 6, the bit number 5. 8 is the very simplest number where you get the most significant bit as 1. Okay, 8 is the only number where you get the most significant bit as 1. Other than that, if you go higher above that, you get 1001. Whatever number you take, you have additional logical ones apart from the most significant bit. So that's an extra for me. And if you go below this number, for example, say 7, you won't have the most significant bit as 1. Okay, in this case, even if you get an output of logic 1 in other number, for example, if you're comparing some other number and that particular number is having most significant bit as 1, and because of this difference, when you do the logical AND operation, definitely you're going to get 0. That means even if you have a negative number, it will be considered as a positive number. So in order to cover all these differences, what we are going to take is we are going to just take the 80 decimal value, hexadecimal number. Okay, now to this number, whatever number we want to find, whether it is a positive or negative number, say some x number. Okay, now say some x number. If we want to find whether this is a positive or negative number, we are going to test this x number with the value 80h. Okay, irrespective of that x. That's what we have done here. That's what we have done here. We have taken the number 87h and then we have tested it. So we have done a logical AND operation with the 80h number. Okay. And then we have checked whether the most significant bit is logic 1 or not. For that, what we have done is we have just used the command JNZ. Okay. So this is another confusing aspect. Keep in mind this one, this particular thing. Keep in mind this particular thing. Okay, now what here we are trying to say is J N Z. That means jump, okay, when not 0. Okay, so jump when not 0. This is linked with the 0 flag. This is linked with the 0 flag of 8086. Okay. Uh, Bear with me with this. So I hope you are clear with this because there's no other option. I have to just delete this. So for that, for clear explanation of for JNZ. Okay. I hope you have understood up to here why we are using 80H and keep in mind this number or else we will do the calculation of this again. Okay. So first of all, let us do the calculation and then we will go for the next command that is JNZ negative. Okay. So JNZ negative is jump when not 0 to the negative label. That's negative is nothing but a just that's just a label. Okay. And what I have done here is if you did not found that JNZ condition is found to be wrong, move to the positive. That means display the value 01h or else display the value 02h. Then jump to the this part of section where you close the program. That's the whole program. Now you need to understand what is the purpose of JNZ. If you understand that, you are completed with the program. Okay. The very first thing that you have to know here is JNZ. JNZ means jump when not zero. Okay, this is the very first thing that you have to know. That's the abbreviation of JNZ. Now, what this function does is this function is basically connected with the zero flag of 8086. Okay, so JNZ is connected with the zero flag of 8086. What this zero flag tells us that if you have done any logical operation, okay, you have done any logical operation, and the result of that logical operation, is zero, only then this zero flag will go high. Okay, keep this in mind. We are going with an example here. Let us take the example here, 87 and 80, this only 80. So let me write the what we say binary forms. See, 1 0 0 0, and what I have here, 7 means 0 1 1. So this is 1 0 0 0 and then 0 0 0 0. Okay, red. So this will show me the difference. 1 0 0 0 0 0 0 0. Okay, so here when you see here, this is the result. Definitely, this is the result of the logical operation. Okay. Now, when you observe all the 8 bits, this is completely zero, but this is not zero. There is the most significant bit which is not equals to zero. Okay. In this case, the zero flag will remain zero. Okay. That means not zero. Oh, sorry. Zero flag. Yeah. It's zero flag equals to zero. Zero flag equals to zero. You might get confused here. This means zero flag equals to zero means it's all the result is zero. No, it's not the meaning. It's not like that. Zero is equals to zero means zero flag. Let me write this here flag. If the zero flag is at logic zero, if the zero flag is at logic zero, that means your result is not zero. Let me try the example of 07 and 80. That means I have 0000 0111 and ATH is 1 0 0 0 0 0 0. Right. Now, if you do the logical and, all the 8 bits you will get are 0. Okay. This will trigger the zero flag, and the logic of zero flag, that means the logic of zero flag will be at logic 1. Okay. Now this will tell that your result, whatever you have done the operation, the result of that operation is all zeros. All zeros. In that case, when you observe the most significant bit, definitely it's a zero. That means it's a positive number. In that case, these lines are going to be executed. For in this case, when you have not zero result, then it's a negative number, and these lines are going to be executed. Okay, clear? I hope you're clear with this. And this is the most confusing part, J and Z. Okay, so JNZ is the most confusing part of the complete thing. You will be clear, you might be having a clarity of this test function, but when you go for the JNZ, it's a very confusing part. Okay, for this, what we are going to do is we are going to execute the program now in both the cases. So let me just copy this all. I'm going to copy this all, and I'm going to open the DOSBox. Yeah, the shortcut. I've got the shortcut. So this is the program that we are trying and testing today, and If you keep this line as it is, you are going to get a error. Let us see that. So I'm going to save this as PRN, okay, pon.asm, or we go for nop.asm, negative or positive. That's it. Now, file, I've saved it, I have exited it. Now, CLR. Now, what I'm going to do is I'm going to create a link file with the MASM nop.asm. So we got an error. What's that error? Where is that? In line number 1, expected instruction or directive. So edit nop.asm. Yeah, that's the line. Alt save, Alt exit, MASM. Yeah, what you have to do is you have to observe one thing here. What is the number that we have given here? It's 87. So definitely you will get a positive number, because no, you get a negative number because 8 and you are testing with 8. So in that case, your most significant bit will get logic 1. That means it's a negative number. So exit. So if it is a negative number, observe here, if it is a negative number in the higher in the higher, what we say, higher byte of accumulator register, you should get a value of 02. Okay. Uh, and if it is a positive number, you have to get 01. So definitely we will get 02 because our most significant bit is going to be a negative value, because we are doing logical AND of 8 and 8. For that, so I'm going to exit from here, MASM nop.asm semicolon. Yeah, no errors. What I'm going to do is I'm going to link nop.obj semicolon. Yeah, linking is complete. Af debug nop.exe. So yeah, my program is loaded. Clicking on F1 so that AL will be loaded with 87. So this function, I'm not loading AL with 80. I'm just testing the value that is present in accumulator register, lower byte of accumulator register, with the value 80. So yeah, if you observe now the zero flag, I won't be able to move this to zero flag, I believe. So F7 will shift this to upward, and F10, which, yeah, if you observe here, then goes down, 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 F8. It has gone there. Okay, observe the flag value at zero flag, that is ZF. Okay, so no, I'm not able to move the mouse also. Here you cannot use this. So if you observe the zero flag ZF, it's 0. That means my result is 0. Now JNZ, when not 0. So my result is not 0, and because my result is not 0, the zero flag is at 0 logic. Now what I have to do is, the commands that are at negative position, negative label, those are going to be executed. That means I am going to get a 02 value, 02 hexadecimal value in the upper byte of accumulator register. See, it has jumped to that part, 02. That means it's not a negative number, it's a, sorry, it's a negative number. Okay, that's it. So by doing so, we can test that it's a negative number. If it is a positive number, in that case, what I'm going to do is edit nop.asm. Okay, here what I'm going to do is I'm going to just simply shift this to 0. Now, uh, yeah, I hope it's safe. Exit, MASM nop dot MASM nop.asm. No errors. Now link nop.obj and af debug nop.exe. Okay, now 07 is loaded. Observe the zero flag after this thing. Okay, yeah, now you get the zero flag, 0. That tells us that our result, the result of doing the test function, has been 0. All the 8 bits are 0. That's why zero flag is at logic 1, and the JNZ jump not 0 condition is not satisfied. That's why we will get AH01 in higher byte of accumulator register. This tells us that our number is positive number because your most significant bit is 0. That's it. That's the end of the program. Okay. So you can quit from here, and that's the complete program. In order to find if the given number is a positive number or a negative number. Hope you have understood. See you in the next video. Thank you.